All right. So next up, we have Dirk Schulze. He works for Adobe, and he spends most of his time hacking on WebKit as part of his work. So I think today he's going to give an introduction on WebKit development. Thank you, Dirk.
Thank you. So first of all, I was told that the weather is here very sunny, very shiny, very warm, and then I landed in Brisbane yesterday. I hope that I have some nice vacations here in summer, and now it's raining. So again, I have a little of a cough, so if you can understand me, just give me a sign. Most likely I will ignore it anyway. So let's start with the presentation. So first, who of you knows WebKit, or at least a name? Okay, great, that's nearly everyone, so let's go to lunch. No, before I start, just some words about me and my work. So I'm working, as Cameron already told you, for the web platform team at Adobe. So our goal is to make the web better. I think we share this goal with a lot of other companies, so that's a good thing. And we at Adobe, we have, of course, a lot of expertise in graphics and also multimedia, print design, and all that stuff. That's why we are really interested in these kind of media. So I'm working on filter effect specification as well as CSS transforms, SVG, and CSS masking. We have other people working with CSS exclusions, regions, and blending, compositing. So a lot of things that we are working on, and the good thing is we can work together with all other companies as well. But first, what is WebKit? You at least know the name. A lot of people still believe that WebKit is exactly that what you see here. So a window, some buttons, maybe back and forward, I don't know, and a address bar, and then some kind of area that draws your page, your web page. But the truth about it is, actually WebKit is just this part that draws the page in this area. Everything else is a browser. WebKit is a browser engine. So WebKit itself is in use in a lot of browsers. I guess you know at least two browsers, that's Safari and Chrome. There are a lot of other WebKit browsers on the desktop. But on the desktop we share the market with a lot of other engines. So we have Gecko and we have Trident from Microsoft with Internet Explorer, and not sure how, what Opera is using. Presto was it. On mobile it might look a bit different. I think we just have WebKit there. Do we agree? I heard that Mozilla is working on something as Firefox OS. Is it using WebKit on the hood?
It's also Trident on Windows Phone.
Yes, well, yes. But the truth is, so WebKit has a very high market share on mobile, and right now we have Android that's using WebKit with the Android browser or Chrome. We have iOS with Safari. We have BlackBerry. BlackBerry still has some market share, and they are also using WebKit. And even some Nokia phones still use WebKit with Windows, not Windows 8 phones, or not even with Windows 7 phones.
My WebOS pre-runs WebKit. I just wanted to make sure that WebOS was mentioned.
Oh yes, sorry. So a short history. WebKit is actually based on KHTML and KJS, two projects from KDE, from the KDE guys 2,000 years ago, whenever they developed it. I think 1998, so nearly. And Apple ported it to macOS X in 2002. And, well, announced it officially at the Macworld Expo 2003. Later, in 2005, it was also published open source, and now then the domain webkit.org was mentioned, and developers were able to actually develop on WebKit, and a lot of KHTML guys actually did it. Later, KSVG2 was added, and then we had first capable browser that was supporting HTML, CSS, JavaScript, as well as SVG, some kind of graphics. So that's about the history. Now we come to the contents. So WebKit does not just exist as a monolith giant program. It actually consists of different parts. One part is so-called web core. Web core is responsible for triggering the loading of pages, for actually drawing these pages, means calculating the layout, drawing it on the screen, and a lot of other things. WebKit tries to be as platform independent as possible. So you will most likely or very seldom see some code that actually is based on platform code. That's something that we really try hard to do. And sometimes we fail, especially when it comes to graphics layer, which we have the discussion before. And another part is the JavaScript engine. So as mentioned before, the JavaScript engine originally is based on KJS and then called JavaScript Core. But some browsers like Chrome use another JavaScript engine. In this case, it's V8. And together, so Web Core and JavaScript Core have some bindings so that they can actually work together. JavaScript is able to manipulate websites so that you are able to create web applications. And then there's a third part. I call it WebKit because it mainly stays in the WebKit folder, in the WebKit repository. And the WebKit folder is actually the folder where all the platform-dependent stuff is inside, with one exception, but that doesn't matter. And that means everything from really loading the page, from accessing the graphic library, and everything is inside this called WebKit component. And everything that's really platform-specific must be in there. So for instance, we support different graphic libraries. We support color graphics, core graphics, Qt, so Qt, and Skier graphics or Skier is one of the other graphic libraries. We support also OpenGL for drawing 2D even. So there's a lot of stuff that we have there inside and a lot of platforms which actually make it really, really difficult to ramp up all ports that we have together in one engine. That means if you compare some browsers, maybe Chrome together with Safari Mobile or whatever, then you realize that these are really different browsers, just because the platform-dependent part is a bit different. But in this talk, I will just speak about Web Core. So first, we have our web document. This consists of markup. So we have HTML, we have XML, SVG, MathML. All that needs to get parsed, structured, and a tree or something like that. It needs to be structured somehow so that it can be read. Then we have CSS for styling. There are also styling languages, but I think in the web currently the winning part is CSS. And then we have JavaScript, of course. And all three components together create our web document and are used to build our web pages, our web applications. So just take a look at how an HTML document, for instance, looks like. And something that is really interesting, even if you look at the Gecko code, if the WebKit code, it doesn't really matter. We all try to implement specifications. That's a good part. And it is not really surprising, or maybe it is, that the engines and the implementations are really based on the text, on the specification texts. That means, for instance, if you look at this page here, you have the first tag that you see is HTML tag, which gets transformed to an HTML element, which stores all data. This is a DOM element. Then we have the HTML head element, HTML script element, and it goes and continues. So each element actually has a responsible DOM element. And this is all according to specifications. So I mentioned it before, these DOM elements need to be structured somehow. So therefore we need a tree, and we call this tree DOM tree. This is also, just open one of the specifications from HTML or SVG or any XML language, you will see that this is actually just the specification. We follow the specification with implementing that. But one very important difference here is that we do not only have the DOM tree, we also have the so-called render tree. So where is the difference? The DOM tree stores all information that you can read over JavaScript with the bindings that you can, for instance, the attribute values or the ancestor, descendants, and all that stuff, siblings, can be read with JavaScript and is in the DOM. The render tree, on the other hand, really just stores the graphics data. So everything that needs to be known to actually draw it, to actually draw your element on the screen. Here's a short comparison. So every DOM element that gets rendered, that gets drawn on the screen, has a render object. This render object stores all the necessary data, as mentioned before, and therefore it also incorporates the style. It also incorporates the CSS style to calculate these data. But there are also elements that don't have a renderer. For instance, the head element is one of them. The head element consists of very important data, the title of the page, the author maybe, metadata that are used for getting the encoding of the page. But the head element itself does not get rendered. It does not get displayed on the screen. Therefore, it does not have a renderer. Another part is, for instance, if you have special styling. One of these parts is display none. Display none actually disables the rendering. It disables the drawing on the screen. So when we disable it on drawing on the screen, we also don't create a renderer because, yeah, we don't display it. This actually affects also all all siblings, or how's it called? All children elements. In this example, we have a div box. I hope you can see my mouse here. We have a div box, and this div box consists of p element, a paragraph element with hello world in it. Because the div element itself has the style none, the element p gets also not displayed. Therefore, we don't create a renderer for the paragraph element as well. So, elements usually not painting can get rendered. So here's one element. The script element usually does not get rendered. So why would you need to render a script element? But it is stylable, and with certain styles, you can actually make it render. With this example, you make the script element interact like a pre-element, and it actually gets displayed in the web page itself. So that's how some elements can certainly get a render object even if they don't get one in real life. But there's also the other way around. Not every renderer does have to need a DOM element. So this is not a one-by-one relation. A render object does not mean that there is a DOM element on the other side. This is one example. You have a div box here. This div box has an inline text, hello, here, and another div box with inline text world. For the div box, we create a render object, a render block exactly. That's one render object. It's inheriting from render object, and this also creates a children rendered element called render text here in this case. But you see here that we also create a render block even if there is no div box on the other side. This might sound very confusing. The answer to this question, why we do it, is actually a noun that's called anonymous block. So what is an anonymous block? So that's something that's really confusing. If you want to know it, just read the CSS 2.1 specification. So CSS 2 actually requires that you cannot have an inline children together with a block element. Therefore, you need to create some kind of block element for the inline child and put it in there. And this pseudo element is called anonymous block box in this example. This is just one demonstration that we really just follow the specification. We really just implement what's specified. Okay, we talked about render objects, we talked about DOM objects, or DOM elements. There's another part that's called render layer. So in the first talk today, you may have heard about the render layer in relation to the graphics layer. So what exactly is a render layer? So if you look at this source code here, we have a div box again, and two div boxes or child elements. And one of it has a z-index of 1. What does it mean? Z-index actually allows you to control the paint order. It allows you to place other elements above other elements. So one element above another element. Usually you go along the DOM and just render everything across each other if necessary, or next to each other in this case for CSS. With Z-index you can control and say, okay, no, I want to have this element that's in the DOM first, I want to draw it above the other element. To make this possible, we have to put this render element, in this case it would also be a render block, into a layer and say, okay, this is an extra layer, this gets painted above this other. And that's what we do. And this is also specified in CSS and called stacking context. So in this example, usually we would have render block, this first div box, and then as children renderer, we would also have div element and div element, so 2 render blocks again, one with a style C index, but we split it up into 2 parts with 2 render layers. Render layer is the top, and render layer collects all render objects to draw. So we have 2 render layers, and now we figure out which one we draw first. So we select this one because the index is higher than the other one. And then we create the second render layer and draw the rest above, better. Actually, the ordering is wrong. So we draw first this one, and then we draw this one, just because the index is higher. So, as said before, the stacking context is something that's specified by CSS 2.1 again. So there are several CSS properties that can create a stacking context. One of them is, of course, the index. We talked about that. So another one is opacity, filter, mask. Filter, mask are new properties. Transform is also quite new, but we have a specification that's quite ready. And some specific layout. So for instance, if you have fixed positioned elements, it means that you have an element that is outside of the render content, a render layer, or the rendering of the web page itself. So you actually specify that it should be drawn on a specific point. Then this needs a new render layer for this object that is positioned. There are other specifications like Flexbox or even CSS regions that also create stacking context. It's quite complex and defined in these specifications. But let's take a look at the render object. So render object has 2 very important methods. One is layout and one is paint. So first, let's stay on this page. First, layout. What does layout do actually? For every element, we need to know where it is painted, which dimension it has, and also, of course, some style information like color or whatever. But we are more interested for layout of the dimension of this element, so that we can position other elements relative to it and render the whole web page and layouts the whole web page. So this is why we call render object layout. Render object layout takes into account the parent renderer, the dimension of it. For instance, if you have a div box with width of 100% or something like that, we need to check the parent. And takes a lot of things into account, like styling. If you have width of 100 pixel, then you also need to render it in the proper way. It takes account borders. For instance, if you have a border of 10 pixel, that means the dimension gets actually thicker. And I think I should just give an example here directly. So in this case, we have a div box style of width with 100% or no, so 100 pixel and higher of 100 pixel, and a border around this box. So we can actually draw it, and then we see we have this box here, 100 pixel to 100 pixel, and this border around it. And when you could look at the layout rect, then we see it's 0, 0 because of the positioning. It's positioned on the top left, and 210 to 210. So that's our layout rect. We call it layout rect in WebKit. It might be different in other browser engines, but actually everyone is quite doing the same. And this is responsible for the further layout, for instance, for the children. The children now know the exact size of the parent, and this gets recursively into all the children elements. And this also helps us to know which part of the web page needs to get repainted. So we are not repainting the whole page the whole time. So if I change the color of this here, of this rect, then just this rect is repainted. Everything else stays as it is. Otherwise it would be far too complex, far too slow also. And that's why we call it the repaint area and or the repaint rect. And this is also the affected area of painting. Again, so we have the layout, that's something that we talked right now, and then we have the paint method. The paint method, other than the layout method, is really responsible for drawing it. So we got all layout information, we know the size, we know the dimension, we already know the style, we know that it has a background of black, white, or whatever, we know the color of the border, we just want to draw it. And that's actually what paint is for. It just draws it on screen. And we do it actually in different paint phases. So each render layer calls different paint phases, and each paint phase calls the paint function. So first we draw the paint, the background and the borders. That's the paint phase. Then we have the floating content, paragraph for instance. And then we have the inline content that might overflow the floating content. And all these three paint phases require that you call the paint function multiple times. The good thing on that we have the paint and the layout functions separate is that layout does not need to be called all the time. So for instance, background change doesn't need to get a relayout. We don't need to recalculate the rects all the time, all the children, everything, all and over again. It would actually be really painful and really slow. So we really just want to repaint a rect and its content maybe if we just change the color. And that's what we do here. So we have, the paint phase is just called when, or it's not only called when you have changes on colors or whatever, and the layout phase is, in this case, is not called. That makes it actually more effective. So the whole concept of paint phases and layout is actually also based on CSS boxing model. So again, we follow the specification as far as we could, as far as we can, and we will do it in the future as well. So beside paint and layout, there's a third function that is really from interest, and that is for hit testing. So sometimes you might have pointer events like hover, or even JavaScript based on mouse over or something like that. And for these paint phases, you need to know where your pointer of the mouse is. For instance, when I go over here, the engine internally checks where my mouse is, which element is selected, and if there's anything that's best on this position. So for instance, the hover over this element here should trigger something. That's why we always check where the pointer is. Every element gets always checked. Is the mouse pointer there in your repaint area? Does it affect anything? Does it trigger any dynamic changes? And to do this, we have also a function called node@point. So every time you move your mouse, we call this function, and it actually checks if there's any change required just because of you moving your mouse. So HTML layout is really complex. So we have the CSS boxing model, and we have these curious things like anonymous block. We don't have things like that in SVG. SVG is a bit different. SVG is a graphics format and not a layout format. That's why we also don't need things like boxing model there in theory. We also have some difference there because mostly every element is actually drawing something or responsible for drawing, and therefore every element has a renderer. There are exceptions like the display none case where we also not create a renderer, but in general, even for groups or for the box devs, I'm not sure if you're familiar with SVG, all these elements create a renderer on SVG. So as mentioned before, we don't have a CSS boxing model, and therefore we also don't care about anonymous blocks and inline elements, with exceptions. So we have the text element. The text element uses the rendering of HTML a lot. And you can use T-spans, which is actually similar to span in the HTML world. So there are exceptions. Mainly, these are really restricted. So if you want to create a new interface, a new element in WebKit, then the first thing that you should do is take a look at the specification, read the specification, read what is expected from you, what is expected from the implementation. Then if you implement an interface or an element, then there's most likely an interface description. This interface description is written nowadays in WebIDL, so we have a talk about WebIDL later this day. And here's one example of SVG 1.1. This is not WebIDL, that's a previous version of IDL, but also describes how an interface. So we have the element SVG element. It's inheriting from element and has some attributes. Here in this case, it's set-race, or no, sorry, ID, XML base, and so on. So that's XML specific. But we also have owner SVG element, which always gives you the SVG element, so top SVG element of your current object. And if you want to implement an interface like that, you should just do it. So now it comes to the code examples, where I demonstrated. One moment. Just need to check, is it big enough? This is exactly the IDL that I had in this short image. So you see a lot of things that were in this image before. So you have the interface SVG element, it inherits an element, it's the same syntax. It has some specific code here in these brackets. This is WebKit specific. In this case, it's also JavaScript specific. So you see some V8 stuff. So it just affects the V8 JavaScript implementation. And then you see exactly these DOM strings, attributes, ID, and XML base. You also see owner SVG element, viewport element. So everything is exactly the same, and we have code that auto-generates the bindings for JavaScript to access the DOM based on this IDL. If you implement the element itself and you create the class SVG element, say that's inheriting from something. In this case, we have an instance between SVG element and element called style element. But fact is, you still see the XML base function here, which returns a string. You still see the SVG element function, which is implemented as an attribute, and the viewport element. So we again follow the specification in this case, and it's really easy to read this code just because of this knowledge. The knowledge of the specifications, the knowledge of how implementations work. And when I just look here as an example, so you find the fill function. No, I don't find it. Paint. Here's a paint function that is called, and it checks the repaint rect if something is even needed, if a repainting is needed, if the content that needs to get repainted is inside of our own repaint rect. If not, then we just quit. And then it just calls the child elements, or child renderer in this case, and says, okay, please render whatever you have to render. Please display it on the screen. And it also has the layout function, which checks if a repaint is needed. In this case, it's render SVG container element. This is a G element similar to a div box in HTML, just a grouping element, and it just checks if the children elements have changed their size. If they change their size, then we also need to change the size of the group element so that we have an actual data of the current repaint rect and all that stuff. So it's very easy to understand the code once you know how it's structured. That's the important part always. And then we also have a short example of node at float point. Node at float point is the function that checks for your pointer. It checks if a pointer is on your element and it reports back. So you have the hit test request and then you have the hit test result, which says, okay, I'm actually resulting on, or I'm the element that's actually resulting on a pointer event, and fires back to the caller and says, okay, I was hit. Here we also have some special handling. SVG has some kind of pointer events where you can specify, I just want to have, from an element, I just want to have the painted part, I just want to have the border, I just want to have the fill part that's selected. So we have very specific commands. These are exposed in HTML as well for WebKit. Other browsers might follow, might not. The specification is not going forward yet, so we will see. And I mentioned before that the transform code in SVG is quite different. So SVG's transforms are a lot older than the CSS transforms. Our implementation is based on KSVG, which is also nearly 10 years old now. So we have some specific handling for transforms. In this function here, calculate local transform, we check the current element, we calculate the transformation, and update our repaint rects according to these elements, according to the transformations. And I think that's about it, what I would like to talk about for now.
That's enough for you to all go ahead and start hacking on WebKit? Or? It's interesting actually to see the similarities between Gecko and WebKit in terms of actual like C++ object for the DOM tree, a render tree which we call a frame tree. We also have a layer tree for exactly the same things like opacity and filters and other things that need to be composited separately and put up to the GPU.
Something that I should mention in this case, the render layer is actually based on the Mozilla project. Project.
Happy sharing. All right, any questions?
It's the benefits of open source.
Yes.
Hi, can you talk about how a dynamic element such as a animated GIF or a video notifies the render tree that it needs to be repainted?
Actually, the video element is a bit specific. For the video element, we have information about the playtime, about the current time, and all that stuff. But it's isolated, hardware isolated. That means it gets drawn by the platform code and doesn't need to get a repaint. So the repaint is handling this specifically. Now, the relayout or the layout is handled the same way as an image element, but the painting is just called once because the rest is handled by the platform code itself. So we don't call paint function for every frame or something like that.
Any other questions?
Is the render tree completely rebuilt for any change to the DOM tree, or can it be done? Is it optimized?
That's actually a good question. So yes, we need to rebuild it partly. For instance, if you change the parent element, then all the children need to be rebuilt. If you have display none, then we also need to rebuild parts of it. I don't think that we rebuild it completely.
I think it's the same in Gecko as well. Like, if you just change the color, then you don't need to recreate all the frame objects or the render properties. But if you change like the display property to change the development into sort of a table cell or something, then you might need to.
Yeah, so for style changes, we don't create. We create a render tree. Then we state, with the exception of some element, properties like display. But if you dynamically add an element or remove an element, then this affects the render tree as well, of course, and it gets partly rebuilt then.
But only partly. You don't need to completely trash it and rebuild it.
No. Well, I assume no. I don't know.
Yeah.
How much of an impact does the platform stuff in WebKit have on how things are rendered on the screen? Because I've seen, for instance, two different WebKit-based browsers on a mobile platform. One had an issue with rendering background images, and the other one was fine. So I guess that part of the rendering must have been in the platform-specific bit of each browser's code, not web core.
The first problem is that the WebKit engines that are used by the specific implementations are quite different, so they are in a different state. So you might see a bug on one that's fixed on another one. And yes, even for painting, everything can be different because of the different implementations for the graphics part. So we have an abstract class called graphics context, which just calls the necessary methods on the platform, but they can still be implemented wrong.
I had a very similar question, but I've come across a bug in mobile WebKit where if you draw a very large extruded box shadow on an object, it does affect the layout. That's only on mobile WebKit, but it is on fairly recent builds of various browsers. Can you hypothesize why it would be affecting the layout?
Yes. So the question is, what actually does require a relayout? Does shadow, for instance, require layout? So no, it doesn't. There are properties, and that's need to be checked with every specifications that require layout. Width is one property, for instance, high, that definitely requires a relayout. Same thing like shadows don't require a relayout, or they don't require a page relayout. It does mean that the painted rect, of course, changes with the change of the shadow. So if you make the shadow bigger, then the repaint rect changes, of course, to the size of the shadow. If it does not work that way, then it's a bug.
When I filed the bug, what's the best hypothesis for the source of the bug?
So we have different components in Bugzilla where you can file it, for instance, CSS, SVG, rendering, layout, and this part would probably go to CSS.
Any final questions?
So I've got a couple of questions regarding kind of edge cases. First is Shadow DOM. Is the render tree any different with Shadow DOM elements at all?
I'm not really a Shadow DOM expert. I can't really answer questions to that. So as far as I understood, the Shadow DOM for us in WebKit is creating a render tree, and which is separate from the render tree that you have in your real DOM. But after, it does not really build a DOM tree, as far as I know.
So the same would be roughly true if I have an SVG with like an HTML foreign object in it or something, and then that's painted as the background of an HTML element in a document, or for instance a canvas is then set as the background through CSS or something like that. There's to the best of my knowledge, like a WebKit specific. I think Mozilla has an equivalent for Gecko, but there's no standard. You set a canvas that exists just by ID or by the name of JavaScript object.
I don't get your question yet.
Context for canvas from the background of an element and then draw straight onto that. And so that's similar to the way the Shadow DOM works with a completely separate render tree. And then that is kind of, once painted, brought into the main render tree for the document.
That's a very specific question. I can't answer that.
So my impression of Shadow DOM is that you would need to keep the render tree around, because even though you might have content which is inside the shadow tree, you still need to be able to select it and interact with it, because if you have like a button component or something.
But his question was specific about the background property, where you can add a canvas element as background. But I think in this case you have the canvas element. It is either in the DOM directly or not, but it's not really specific to a Shadow DOM. It's something different.
If you're painting an SVG thing to a canvas and then you're using that canvas as a background somehow, is that what you were doing? Like creating a blob URI?
I think it was kind of two separate questions. So the Shadow DOM thing and SVG and canvas were two kind of separate examples.
Yes.
To ask a question about if you're bringing in content from a foreign document or from something that isn't necessarily kind of simply included in the one tree.
So
does it kind of bring in a new tree and extend the main document tree?
To make it simple,
A completely separate tree, get the render result from that, and then just paint into the other one.
Yeah, to make it simple, your example where you have an SVG document that you put on the canvas, this creates a DOM tree internally. It's a new document, and it's just painted into the context. So we create a DOM tree internally and create a render tree for it, yes.
By the way, the same for Shadow DOM. We have a Shadow
That
group
is-
and a Shadow DOM in the other.
The Shadow DOM is a bit different, I guess. Again, I'm not an expert in the Shadow DOM. Not in our implementation, at least.
Yeah, you can activate it in the inspector,
Mhm.
and you can turn it on, and it looks exactly like it's part of the DOM, and it also has its own render tree.
In this case, it must create a DOM tree as well.
Yeah.
Okay, so with that, thank you again, Dirk.
So as mentioned before, the JavaScript engine originally is based on KJS and then called JavaScript Core. But some browsers like Chrome use another JavaScript engine. In this case, it's V8. And together, so Web Core and JavaScript Core have some bindings so that they can actually work together. JavaScript is able to manipulate websites so that you are able to create web applications. And then there's a third part. I call it WebKit because it mainly stays in the WebKit folder in the WebKit repository. And the WebKit folder is actually the folder where all the platform-dependent stuff is inside, with one exception, but that doesn't matter. And that means everything from really loading the page, from accessing the graphic library, and everything is inside this called WebKit component. And everything that's really platform-specific must be in there. So for instance, we support different graphic libraries. We support color graphics, core graphics, Qt, so Qt, and Skier graphics, or Skier is one of the other graphic libraries. We support also OpenGL for drawing 2D even. So there's a lot of stuff that we have there published open source, and now then the main webkit.org was mentioned, and developers were able to actually develop on WebKit. and a lot of KHTML guys actually did it. Later, KSVG2 was added, and then we had first capable browser that was supporting HTML, CSS, JavaScript, as well as SVG, some kind of graphics. So that's about the history. Now we come to the contents. So WebKit does not just exist as a monolith giant program. It actually consists of different parts. One part is so-called web core. Web core is responsible for triggering the loading of pages, for actually drawing these pages, means calculating the layout, drawing it on the screen, and a lot of other things. Web core tries to be as independent as possible. So you will most likely or very seldom see some code that actually is based on platform code. That's something that we really try hard to do. And sometimes we fail, especially when it comes to graphics layer, we have the discussion before. And another part is the JavaScript engine.
All right. So next up, we have Dirk Schulze. He works for Adobe, and he spends most of his time hacking on WebKit as part of his work. So I think today he's going to give an introduction on WebKit development. Thank you, Dirk.
Thank you. So first of all, I was told that the weather is here very sunny, very shiny, very warm, and then I landed in Brisbane yesterday. I hope that I have some nice vacations here in summer, and now it's raining. So again, I have a little of a cough, so if you can understand me, just give me a sign. Most likely I will ignore it anyway. So let's start with the presentation. So first, who of you knows WebKit, or at least a name? Okay, great, that's nearly everyone, so let's go to lunch. No, before I start, just some words about me and my work. So I'm working, as Cameron already told you, for the web platform team at Adobe. So our goal is to make the web better. I think we share this goal with a lot of other companies, so that's a good thing. And we at Adobe, we have, of course, a lot of expertise in graphics and also in multimedia, print design, and all that stuff. That's why we are really interested in these kind of media. So I'm working on filter effect specification as well as CSS transforms, SVG, and CSS masking. We have other people working on CSS exclusions, regions, and blending, compositing. So a lot of things that we are working on, and the good thing is we can work together with all other companies as well. But first, what is WebKit? You at least know the name. A lot of people still believe that WebKit is exactly that what you see here. So a window, some buttons, maybe back and forward, I don't know, and a address bar, and then some kind of area that draws your page, your web page. But the truth about it is, actually WebKit is just this part that draws the page in this area. Everything else is a browser. WebKit is a browser engine. So WebKit itself is in use in a lot of browsers. I guess you know at least two browsers. That's Safari and Chrome. There are a lot of other WebKit browsers on the desktop. But on the desktop we share the market with a lot of other engines. So we have Gecko, and we have Trident from Microsoft with Internet Explorer, and not sure what Opera is using. Presto was it. On mobile, it might look a bit different. I think we just have WebKit there. Do we agree? I heard that Mozilla is working on something as Firefox OS. Is it using WebKit on the hood?
It's also driving it on Windows Phone.
Yes, well, yeah. But the truth is, so WebKit has a very high market share on mobile, and right now we have Android that's using WebKit with the Android browser or Chrome. We have iOS with Safari. We have BlackBerry. BlackBerry still has some market share, and they are also using WebKit. And even some Nokia phones still use WebKit with Windows, not Windows 8 phones, or not even with Windows 7 phones.
My WebOS pre-runs WebKit. I just wanted to make sure that WebOS was mentioned.
Oh yes, sorry. So a short history. WebKit is actually based on KHTML and KJS, two projects from KDE, from the KDE guys 2,000 years ago, whenever they developed it. I think 1998, so nearly. And Apple ported it to Mac OS X in 2002. And well, announced it officially at the Mac World Expo 2003. Later in 2005, it was also